But that's what your 30 box model will look like. And okay, so now let's look at the upwind and the quick schemes. As I said, if for any box, for any face, this is a face right here. So what we want is, we want the concentration of material that flows across that face. And if you're using upwind differences, we simply go to this box right here. And since the flow is in this direction, we take the concentration in this box and use that as the concentration at that face. Very simple, but not particularly accurate. As we'll see, it has a lot of advantages later on. This is a diagram, if you will, of quick or quickest. And as I said, what we're going to do is, if we want the concentration that flows across this face, we take two boxes upstream and we take the actual box in which we're interested in and we fit a parabola to it. So the concentration at this face is, if you will, a function of these three cells. Now, okay, fair enough. Suppose the flow were going the other way. The concentration would be this cell, and this cell. All right, so you'd want to do it like this. If the flow were going the other way, you'd go one, this cell, this cell, this cell, and you draw a parabola. The reason I'm pointing this out is, a little later on, remember I told you that a box, the only thing it knows is who's next door and who lives upstairs and downstairs. What you have to do is, for any face, if you will, you need to know a total of 4 boxes. The two to the left of the face and the two to the right of the face. And the reason you have to know 4 boxes is, if the flow is going in this direction, you need to know this 2 upstream, 1 upstream, and the actual cell. If the flow is going in this direction, you need to know 2 upstream, 1 upstream, and the actual cell. So for any face, you need to know 4 boxes in order to use quickest. Okay, what else do we know? Okay, so once again, remember that...
Quick question if I can, Carl?
Yeah, go ahead.
Just because we don't use quickest. When you get to, you know, if you could go back to your previous slide for a minute. Suppose box IL happens to be a land cell. What does quickest then do? It just uses the actual and the upstream and...
We default to upwind, and that's built into the code, and we will get to that.
Okay.
But yeah, that's why, well, we default to upwind.
Okay.
This is a small piece of that 30 box model that I showed you a few moments ago. And yeah, I gotta watch my own thing here. Okay, so for box 1, just note that there's no, you have a flow 1, a flow 2, a face 1, a face 2. This happens to be face 33, face 32. You know, keep in mind, I just repeat myself, there's no IJK. You know, you can't, if you're looking at the code, you can't just subtract 1 and think you're at the next box or something like that. So all of what you have to do is, and we'll get into this, you know, you have to create something we call a map file, which details all of these, you know, for any face, who's connected to me, who lives next door, that sort of thing. So we'll get to that, but just keep in mind that this is how it works. Okay, we won't go there yet. So we'll come over to here. So let's see what else we know. So, you know, just as to mention, so if you want to do advection, you need you need to provide the model with the cell volume, with the indices of the faces, you know, the flow across the faces and the length of the cells. So these have to be provided in some fashion. they're provided in two fashions. Actually, some of them come from model input files, like what we call the map file, and some come from the hydrodynamic model. We'll get into that.
And one more, I'm sorry, one
Go
more
ahead.
question. So when you talk about the length, you need to provide length in both directions, because you know,
Right.
and actually a Z, right? All three.
Yeah.
Okay.
But to do longitudinal and lateral,
Right,
you need
okay.
just that one. Eventually, you need the others. That's correct. Dispersion, I'm not going to say a whole lot about dispersion. Okay. Basically speaking, I won't go into the details. This quick will also do some approximations in order to do dispersion, and I don't want to get into that right now. But it's fairly simple. We need to know the derivative. We need to know the gradient at a face, and the gradient at a face is simply the concentration in two boxes divided by delta x. So, you know, that's not particularly hairy or not worth detailing. Now, remember that I said that we do these in pieces. You know, we solve this three-dimensional conservation of mass equation in pieces. So the first thing we did was we took the longitudinal and the lateral advection. Now we're going to do vertical transport. So we're going to do it in two pieces. In the vertical, so let's see what we do. Let's look in detail a little bit. This index, t plus delta t, means the future time step. That's the unknown you're solving for. This one, c sub j star, that's the intermediate result that we obtained when we did the longitudinal and lateral transport. So now what we're saying is, this derivative, if you will, the concentration of t plus delta t minus c sub j star divided by delta t. Okay, now, remember that what we need to get in order to do this equation is we need the concentration at the faces. Now we're going to talk at the two vertical faces. Okay, so there are two issues in how we do that. One is, remember that the model takes concentration at cell center, so we have to interpolate in some way in space to get the concentration at the face. Now, what time do we take those at? Right? Do we take them at the previous time? Do we take them at the future time? Do we take them somewhere in the middle? Okay. So what we do here is you see that this is flow times concentration divided by volume. So that's a change in mass, a change in concentration. We've got this thing theta. And you'll see that what we're doing is we're saying that the change in concentration here is something based on the concentration at the present time and something on the concentration at the future time step. So what we're really doing is we're interpolating between those two times. And I won't go into all the details of this right now. Those of you who are familiar with numerical methods, you know that there are stability requirements when we do these things. Okay, when you take a differential equation and you digitize it to solve on the computer, there are a lot of constraints in there having to do with stability and accuracy and such. And unfortunately, we didn't worry about that in the longitudinal and lateral because we didn't have to, but in the vertical, we need to worry about it. So what theta does is theta weights, if you will, between these two time steps. If theta equals 1, what you see is we're going to work exclusively with the future time. And that's a fully implicit numerical scheme. I'm dropping buzzwords, but for those of you who are familiar with that sort of thing, that's a fully implicit scheme. We like fully implicit schemes because they have good stability properties. On the other hand, we don't like them because they have a lot of numerical diffusion associated with them. They have some undesirable properties, okay? So they're stable, but they have undesirable properties. On the other hand, if we made theta 0, it would be what's called fully explicit, and we have a lot of stability problems. So what you can do is you can, if you're applying ICM, you can weight theta, and it's sort of touch and go. You know what I mean? But you typically, ideally, you make theta 0.5 or something like that. It's touch and go. It's trial and error to get a theta where, on the one hand, you get a stable solution, but you don't get too much numerical artifact. And typically, I think theta for the model we're using is like 0.7. So it tends to be towards the implicit end of things, but not fully implicit. So I mention this because, well, when we look at the control file, you're going to be asked to specify a value of theta. And, you know, if you're actually going to run the Bay model, it's not a problem because it's done for you. But if you're going to apply this model to some other system, then you're going to have to worry about that.
Sorry to interrupt with a question.
Go ahead.
If you ran fully implicit, then it just makes this too much of, it reduces the gradient between surface and bottom too much?
Yeah.
Oh, okay.
Yeah. Okay. And I think, well, what you see over here is that this is the diffusive transport term, and we run that one fully implicit. We don't give you an option, and the reason is, like it or not, you need the stability, okay? You can really, if you think about these cells, you know, they're order magnitude a kilometer in length and breadth, and they're order magnitude a meter in thickness. So the stability requirements you know, can be very different for the longitudinal and lateral versus the vertical. And so, you know, what I'm saying is we just know in advance that if you don't run fully implicit vertical diffusion, you're going to get headaches, okay? So we don't give you the option. It's just the way it is. Let's see. I don't want to move on. Okay, so this is just a list of, just tells you what you have to supply if you're going to do the vertical. If you want to solve in the vertical, you need the indices of all the cells, the indices of the flow faces, the volumes, the flow across the index flow faces, the diffusion coefficients, and the length of the index cells. And once again, those will come to you from either the hydrodynamic file or from a file like a map file or a geometry file or something that you're going to input to the model. Let's see. So there's a summary, if you will, of how to solve this equation. Now, you don't really worry about this. The model code does this, but I'm just explaining to you what the model code is doing. And what it's doing is, first, it's going to evaluate the internal sources and sinks. The kinetics, transformation, the sediment water fluxes, these sorts of things. Next, we add in the external loads, the watershed, the point sources, these sorts of things. Next, we solve the longitudinal and lateral advection. We get an intermediate result, and then we do the vertical transport separately. And once you go through all of these 5 steps, you have advanced one time step, and you've projected from the present time step to the future time step. Let's see what's in this one here. Okay, so we'll talk for a minute or two about a question that Jim brought up before. Remember that for any face, here's a face, if you will. When we want to get the the concentration across this face, if we want to use quickest, we needed two segments upstream and we needed two segments downstream. So that's fine. What do you do if you have a boundary condition? All right, now, if you think about it, there are sort of two things that could happen. One we haven't talked about, but let's just imagine for a minute that this thing right here, this cell that I'm pointing at, that is the most upstream cell in the grid. And upstream of that, there's a river that pours into the system. Okay, so that's about, that's what we call an open boundary. If there's a river that pours into the system, that's what we call an open boundary. We don't have a grid up there. So we can't get two model cells upstream of that boundary because there aren't any model cells upstream of that boundary. Now, a boundary condition is we will specify, for the moment, we'll just say we have a boundary concentration. So what we want to do is we need to specify the concentration at this most upstream face. That's what flows into the system. Now, we hardwire into the code at that face what we've been calling upwind. Okay. At an upstream boundary, this concentration, this specified concentration, is what flows into the system, period. Even if you opt to use quickest. And we do that for a reason, because we don't want to, number one, we don't have two cells up, but also, if we used quickest, this concentration in this box would be one of the three things to which we would fit our parabola. So the flow across that cell, this face, would not actually be the specified boundary condition. It would be, if you will, the concentration in the box downstream would be taken into account when we computed what flows across that face. Does that make sense, or am I just getting way up in I see a nod somewhere, but does everybody get that?
That's good.
When we specify a boundary concentration, we want that to be the concentration that comes in the system, not something that's interpolated, okay? So that's why, and again, you don't have to worry about this, the code does this, but I just want you to understand what the code does for posterity when I'm not here. Go ahead.
So you treat that as external loading or just concentration?
All right, we're going to talk about this in a little while, but that's a concentration. Now, strictly speaking, the flow times concentration becomes a load. But this is just concentration for now. You have a similar situation. So this is an upstream boundary. A river, something like that. The other end, you could have an upstream boundary where things flow out, the ocean. It could go both ways, in fact, but you can have an outflow boundary. And when we get to an outflow boundary, so this is our grid, and this is this is outside the grid. And we hardwire, once again, the outflow boundaries are hardwired, they're upwind. What flows across that face is the concentration in that cell. Okay, I'll just mention again, so go ahead.
Just to understand, the upstream, let's say an upstream boundary, thinking about it like a dam, as you said, a river, there's not going to be any dispersion. On your ocean, do you take into account dispersion?
We do not.
You do not, okay.
We do not.
All right.
And to level with you, I'm not entirely certain what the rationale was anymore, but we do not allow dispersion across boundaries.
All right.
They're a strictly upstream flow. Okay, so yeah, actually, look at that, Jim. No diffusion at open boundaries.
Yeah,
I was thinking you were thinking of those rivers, but I wasn't sure about ocean side. Okay.
Just to expand on that for a moment, what would be the consequences of not having dispersion at an ocean boundary?
Well, think about it, since the models are running intertidal, probably not much, but suppose you did a tidally averaged model. then if the flow was always out of the system, you'd be possibly ignoring some factor of the tides coming back and forth and bringing some concentration back in. So,
I've made that mistake. We've used this, actually we set up a little tidal average model of Lynn Haven Bay, and somebody came to me and the boundary conditions in the ocean did nothing, and it was because we had hardwired no diffusion.
okay, so.
And we had to put it back.
You had to put it back, okay.
Yeah. So that's interesting, but there you go. But for the bay and for am I seeing a questioning look here?
You are. So you hardwire upwind, but upwind is one side, or upwind is the concentration in the cell. That's what's moving out. But suppose water's moving into the cell. If water's moving into the cell from the upstream, what would be hardwired would be the boundary concentration, no?
Yeah, so what happens is, I'm going to move around here to the screen. Let's just make this is the ocean.
Yeah.
Let's just say. So this is the ocean and this is the bay.
Right.
When water's flowing out of the bay, we take the concentration in this cell and move it out of the bay. When the tide turns and water's flowing into the bay, we use a specified ocean boundary concentration.
So you do get you do get at least some of the flow back, because you get the boundary.
No, I understand, but that's because they're doing an intertidal model, but if you did a tidally average, then you wouldn't get it. That was where I was coming from.
A tidally average model, it would only be flow out of the bay, and we run into problems there.
Now I understand the question.
Okay.